डियर स्टूडेंट्स, आज हम कोसेट्स के बहुत ही महत्वपूर्ण थ्योरम पर स्टडी करेंगे। सबसे पहले हम थ्योरम 4 लेते हैं। स्टेटमेंट देखिएगा, इफ H इज ए सब ग्रुप ऑफ ए ग्रुप G, then for any AB belongs to G, AH is linearly corresponding to BH। हमारा स्टेटमेंट थ्योरम शेष 4 का है। H C का एक सब ग्रुप मान लीजिएगा और दो मेंबर A और B बिलोंग्स टू G के लिए हमें प्रूव करना है लेफ्ट कोसेट AH इज लीनियरली कॉरस्पॉन्डिंग टू BH। ये प्रूव करने के लिए हमें यहाँ पर इस बात को समझना होगा कि दो सेट A एंड B आर लीनियरली कॉरस्पॉन्डेंस if and only if there exists a mapping from A to B such that और यूँ कहिएगा कि there exists a mapping from A to B is 1 on 2। This is the definition of linearly correspondence। तो दो सेट ए और बी लीनियरली कॉरस्पॉन्ड होने के लिए यहाँ पर हमें एक मैपिंग एफ ए टू बी 1 on 2 मैपिंग होना चाहिए, ये सिद्ध करना होगा। तो ए एच और बी एच लीनियरली कॉरस्पॉन्डेंस हैं, इस हेतु हमें एक मैपिंग, सपोज हम एक मैपिंग डिफाइन कर देते हैं एफ ए एच टू BH such that F image of AX equals to BX for all X in H। इस मैपिंग F को हम यदि 1 on 2 प्रूव कर दें यहाँ पर, तो हम कह सकेंगे कि AH is linearly corresponding to BH। This AH is linearly corresponding to BH। इसके लिए हमें डेफिनेशन देखनी होगी। 1 कोई मैपिंग 1 कब होती है, इसकी डेफिनेशन देखिएगा। मैपिंग एफ ए टू बी इज 1 इफ फॉर एक्स वाई इन ए, और आप कहिएगा फॉर A1 A2 in A such that F image of A1 equals to F image of A2, then A1 equals to A2। तब हम कहेंगे कि मैपिंग 1 है। सो इस थ्योरम में हम एच जी का सब ग्रुप ले लेते हैं और ए बी जी में दो मेंबर के लिए AH और BH लेफ्ट कोसेट्स के लिए एक मैपिंग डिफाइन कर लेते हैं। F A to B, AH to BH such that F image of AX is BX for all X in H. For 1 1 हम F image of AH1 equals to F image of AH2 ले लेते हैं। By the definition of F, this is BH1 equals to BH2, and by the left cancellation law in group, H1 equals to H2, and then pre-operate by A, we will get AH1 equals to AH2. So we have F is 1. तो 1 1 की जो हमने डेफिनेशन देखी उसके अनुसार ये मैपिंग F AH to BH 1 1 हो जाती है। नेक्स्ट ऑन टू mapping F from set A to B defined as F image of A equals to B for all A belongs to A is called on to if for all is called on to if for all B belongs to B, there exists A in set A such that F inverse image of B is A। ये हो तो हम मैपिंग F को onto कहते हैं। So here for this mapping we have each alpha which is Bx in left coset Bx there exists Ax in AH set AH such that F inverse of alpha equals to Ax. This shows that F is onto mapping. So we here we see that F is there exists a mapping F from AH to BH which is 1 1 1 2. It means AH is linearly corresponding to BH. This is proof of our theorem, and in similar way we can prove that right coset HA is also linearly corresponding to right coset HB for any A and B in Z, and also HA is linearly corresponding to AH also, this one, and we can prove it is easily that AH left coset is linearly corresponding to subgroup H also, and ये नोट और देख लें आप कि if set A is linearly corresponding to B, then order of A equals to order of B. ये किस प्रकार से कि you know that set A is linearly corresponding to set B. It means there is 1 1, there is 1 1 and onto 1 1 onto मैपिंग, इट मीन्स सेट ए में जितने मेंबर हैं उतने ही सेट बी में मेंबर होंगे। तो किसी मैपिंग के 1 1 onto होने से हम ये कह सकते हैं कि डोमेन में जितने मेंबर्स हैं को डोमेन में भी उतने ही मेंबर्स होंगे। सो इफ ए इज लीनियरली कोरस्पॉन्डिंग टू बी, then order of A equals to order of B. So here AH is linearly corresponding to H, so order of H equals to order of AH. Now Lagrange's theorem, जो कि हमारा आज का महत्वपूर्ण टॉपिक है। Lagrange's theorem का स्टेटमेंट है the order of every subgroup of a finite group is a divisor of order of the group. यहाँ हम Lagrange's थ्योरम के लिए हम देख रहे हैं कि order of every subgroup, suppose H is subgroup of finite group G. G is finite, so we can say that let order of G is n and let order of H is m. Then we have to prove that is the divisor of the order of group. So we have to prove m is the divisor of n. This is our m for this term. इसके लिए we know that every group G is equal to union of all left cosets of subgroup of group G. First thing. So, and second statement is that AH either, second statement is that either AH and BH are disjoint or identical. So इसका अर्थ ये है कि यहाँ पर या तो हमारे पास आइडेंटिकल सेट है, लेफ्ट कॉसेट्स हैं जी के जितने भी हैं, और या फिर वो डिस्जॉइंट है। तो हम यहाँ पर जब हम ऑर्डर ऑफ जी एन लेते हैं तो जी में एन लेफ्ट कॉसेट्स होंगे, उनमें या तो सारे के सारे डिस्जॉइंट हैं। सपोज A1H, A2H, ANH और N लेफ्ट कॉसेट्स। अब हो सकता है इसमें से कुछ डिस्जॉइंट नहीं हो, तो उस स्थिति में वो आइडेंटिकल हो जाएंगे। तो नंबर ऑफ लेफ्ट कॉसेट्स यहाँ पर कम हो जाएगा। तो हम यहाँ कह सकते हैं कि A1H, A2H, AKH are disjoint left cossets of H in Z. So G can be written equals to G equals to union of these left cossets. So you can write this equals to A1HU A2HU union of AKH. But and then these are disjoint, so this gives order of Z equals to order of A1H plus order of A2H plus order of AKH. Since AH is linearly corresponding to H, it means order of AH equals to order of H. पहले वाली थ्योरम में हमने देखा है. So here this is order of H, this is order of H, this is order of H k times. So from this we can write order of Z equals to k times order of H, but order of G is n and order of H is m, so n equals to km. This gives m is the divisor of m, or in other words you can say that order of H is the divisor of order of G. This is our theorem. Lagrange theorem. This is our proof of our Lagrange theorem. This one. Let H be a subgroup of group G. Order of G is n, H is m, are identical left cossets or disjoint. N minus k are identical, so G equals to union of XH or this one, or then we can say that order of G equals to order of left cosset, first left cosset plus order of second left cosset plus kth left cosset. You know this one. So order of G equals to order of H plus order of H plus order of H k times. This gives order of H is the divisor of order of Z. So this is very important topic for you. This is Lagrange's theorem. परीक्षा में बहुत बार ये पूछा गया है कि Lagrange's प्रमेय का कथन लिखिए और सिद्ध कीजिए. So this is very important theorem. Now corollary. Depending on this theorem, first corollary is every order of every element of finite group is the divisor of the order of the group. हमें prove करना है. So first, the order of every element. Suppose A is the element of finite group G is of finite order n, we have to prove order of A is the divisor of order of G. ये हमें प्रूव करना है. So for this A, we can say that H is generated by A is a subgroup of group G. We know that if A is the any point of group G, then H generated by A is the subgroup of group G. So by Lagrange's theorem, here H is the subgroup of group G. So order of H is the divisor of order of G. This is by Lagrange's theorem. But you know that if a group H is generated by A, then order of this group is also equals to order of this generator. So you can put here order of A is the divisor of order of G. This is our theorem statement or statement of this corollary. Second, this is corollary 1. And now corollary 2. If G is a finite group of order n and A is the member of G, then A power n is identity. For this corollary 2, let G be a group of finite order n. Here order of G is n, and A is any member of G. So we know that above corollary order of A is the divisor of order of G. Or if suppose order of A is m, then we can say that m is the divisor of n, and this means there exists an integer q such that n equals to mq. Then e raised to power n can be written as a power n cube and a power m power q by power rule. But since order of A is n, it means this gives e raised to power m is identity. So put here e raised to power m is identity power q is identity. This is our statement of corollary 3. like that. The code row corollary statement 2. A raised to power n is identity, this one. Now corollary 3. Every group of a prime order is cyclic. This is also very important statement. Every group of prime order is cyclic. We have to prove, suppose G be a finite group of prime order P. Since P is prime, it means P is greater than 1. So, if order of G is greater than 1, it means there are at least 2 members in G. So, there exists at least one A in G such that this A is other than identity. And so, there is a cyclic group H. We can define a cyclic group H generated by A, which is the subset of G, subgroup of G. So, by Lagrange's theorem, since G is finite and H is the subgroup of group G, so order of H is the divisor of order of G by Lagrange's theorem, or in other words, order of H is the divisor of P. But P is prime, it means either order of H equals to 1 or order of H is P. But order of H is not equal to 1, because if order of H is 1, then it means H have only one member, which should be identity, and so H which is generated by A should be identity E. So, but we already assumed that A is other than identity. So, we can say that order of H is not equal to 1. So, clearly, order of H equals to P, and H is a subgroup of group G, and order of H is P, and P is the order of G. So we can say that H equals to G. By these results, we can say that H equals to G, but H is generated by A. It means G, and which is equals to G. So G is generated by A, and thus we have G is cyclic, generated by A. So we can say that every group of prime order is cyclic. And finally, corollary 4. This is statements of corollary 4. A group of prime order has no proper subgroup. For this, let G be a group of prime order, here P is prime, we have to prove that this has no proper subgroup. Suppose H is the subgroup of G. So we have to prove this H is not proper. We have to prove this H is not proper. So not proper means H is proper, improper. No proper means H is improper. So what is the definition of improper subgroup? So there are only two subgroups. First one is identity and second is itself G are proper, no proper subgroups, that is improper subgroups. These two are called improper subgroups, that is no proper groups. So here we have to prove that either H is identity group or H is G. इस थ्योरम में ये हमें प्रूव करना है. So let order of H is M. We know that by Lagrange theorem, order of H, which is M, is the divisor of order of G. But P is here prime, so either M is 1 or M is P. If M is 1, then in other words, order of H, this M is order of H is 1 or order of H is P and P is the order of G. So we can say that if order of H is 1, then H is identity, or if H is order of H is P, which is order of G, it means H is G. So if P is prime or order of G is prime, then this has no proper subgroup. Means subgroup is either identity or itself C. This is our corollary 4. सो फ्रेंड्स, आज आपने बहुत ही महत्वपूर्ण थ्योरम लेग्रांज थ्योरम के बारे में अध्ययन किया. उसकी 4 कोरोलरीज, बहुत ही महत्वपूर्ण कोरोलरीज परिणाम डिस्कस किए. नेक्स्ट टाइम हम आइलर्स थ्योरम के बारे में स्टडी करेंगे.